Hi, in this video we are going to first derive the impulse response expression of an ideal low-pass filter, and then we are going to use this result for certain representations of band-limited signals. Now, first of all, let us remember the frequency response of an ideal low-pass filter. So the frequency response of an ideal low-pass filter is given as follows: capital H LPF denoting low pass filter action. H LPF of omega is equal to 1 for absolute value of omega less than omega c. Well, we can put an equality here without losing any generality, or we can omit the equality, and 0 otherwise. Okay, in other words, the system action of an ideal low-pass filter is the following. It passes the frequency components of the input signal with frequencies in between minus omega c and rejects the other frequency components. That means omega greater than omega c or omega less than minus omega c. Now, the impulse response of this ideal low-pass filter is small h LPF of t, which is the inverse Fourier transform of the frequency response, h LPF of omega. Okay, so h LPF of t is equal to, okay, we know the inverse Fourier transform integral 1 over 2 pi from minus infinity to plus infinity, capital H of omega e to j omega t integrated with respect to omega, which is 1 over 2 pi. Now the function capital H LPF of omega is only non-zero from minus omega c to omega c, and it is equal to 1 in that interval. So we have 1 times e to j omega t integrated with respect to omega. So this is equal to 1 over 2 pi e to j omega t divided by jt evaluated at omega equal to minus omega c and omega c. So let me continue here. H LPF of t is equal to 1 over 2 pi e to j omega c t minus e to minus j omega c t divided by jt. Now this is equal to 1 over 2 pi. Now e to j omega ct minus e to minus j omega ct is equal to 2j sine omega ct, and therefore we divide by jt. So 2's will cancel out and j's will cancel out. Therefore, the impulse response of the ideal low-pass filter is equal to sine omega ct divided by pi t. Again, a function in the form of the sinc function, but we don't have to write down the expression in terms of the sinc function. It's sufficient to obtain this result. Okay, so up to this point we have considered the impulse response of the ideal low-pass filter, and we have obtained the impulse response by means of the inverse Fourier transform integral. An important observation related to the ideal low-pass filter is that the impulse response is non-zero for all t, for all values of t. Of course, it has zeros because it is the sinc function essentially, but it has non-zero values for negative values of t, which means that the ideal low-pass filter is not causal. So it is not a causal system, because for a causal system, causal linear time invariant system, the impulse response must be equal to 0 for negative values of t. But we have non-zero values for negative values of t, so the ideal low-pass filter as a linear time invariant system is not causal. This is an important observation related to the nature of the system. Now, let us consider a signal x of t which is band limited. In other words, x of t will have a Fourier transform which is non-zero in a band of frequencies, and outside this band the Fourier transform will vanish. So let x of t be a band limited signal, which means that x of omega, the Fourier transform of x of t, is equal to 0 for absolute value of omega greater than omega m. So the band limited signal has a Fourier transform which has non-zero values only in the band from minus omega m to omega m. Now, let x of t be the input signal of an ideal low-pass filter with cutoff frequency omega, this band limited signal x of t be the input signal of an ideal low-pass filter with cutoff frequency omega c, satisfying the following condition: omega c greater than omega m. Okay. Now, since the cutoff frequency is greater than omega m, what will happen if we apply x of t as the input signal of the ideal low-pass filter with cutoff frequency omega c satisfying this property? The output will again be x of t. Okay? So, under this condition, x of omega multiplied by the frequency response h LPF of omega will be equal to x of omega. So x of omega here is the input and x of omega here is the output. The input and output signals will be identical because the cutoff frequency is greater than omega m. In other words, all the frequency components of the band limited signal will pass through the ideal low-pass filter. Now, the interesting expression is the time domain expression. So in time domain, this result can be expressed as follows: x of t is equal to the convolution of x of t with the impulse response. Okay? In other words, x of t is equal to, from minus infinity to plus infinity, x of tau h of HLPF of t minus tau, which is sine omega c t minus tau divided by pi t minus tau integrated with respect to tau. So this last expression is known as, in the literature, it's known as the representation of a band limited signal in terms of the input-output relationship in an ideal low-pass filter with cutoff frequency greater than omega m, which is the maximum frequency of the maximum frequency component of the band limited signal. So we have, in other words, a representation of x of t in terms of x of tau multiplied by time shifted version. We have time reversal and then time shift in convolution. We have the convolution of x of t with the impulse response, and this integral representation is the representation of a band limited signal. Of course, such a representation is not valid for signals which are not band limited. So this representation is only valid for band limited signals. Okay, thanks for watching.